Okay, let's continue on working through the problems in Chapter 1 of Ross as we learn to count that we want to use in probability questions later on. All right, so in this video, we're going to look at 8, 9, and 10. 8 and 9 are very similar and pretty straightforward, and they hit upon a common idea, and hopefully you will see that they are, in fact, the same problem. And then 10 has a little bit more spice to it. So let's start with number 8. So 8, part A, we are just looking at the different arrangements that can be made from these letters. So if we look at A, we're looking at the letters F, L, U, K, E, and they're all different letters. So this is an arrangement of 5 items, 5 distinct items, which is just a permutation of those things. And since we're permuting all of them, it is 5 factorial, right? Or it's 5 things taken 5 at a time. Or 5 options for the first letter, 4 for the next, 3, 2, and 1. Okay, so B is very similar, but as we see here, we have some letters that repeat. So we have P, R, and I'm going to label this P1, R, O1, and then we have another P, so we'll call that P2. We have another O, we'll call that O2, and then S, E. So if these were distinct letters, we would have 7 of those, and the number of arrangements of those 7 distinct letters would be 7 factorial. However, we see that they're not distinct. We have 2 O's and we have 2 P's, and so what this 7 factorial counts is every arrangement including P2, R, O1, P1, O2, S, E. So it would count these 2 words as separate, whereas they're in fact the same word. We can see that they're labeled P1 and P2, but in fact they're just 2 indistinguishable P's. So this 7 factorial is counting every arrangement that includes all the permutations of those P's. So we see that for this arrangement, we actually count it twice because there are 2 arrangements for P1 and P2. So we can fix that by dividing out the overcounts of the arrangements of the identical letters. So since P1 and P2, there's 2 of them, we're overcounting by 2 factorial. So we're going to divide out 2 factorial. Similarly, we're overcounting for every arrangement of the permutations of the O's, of which there are 2 factorial. All right, so this is how we deal with an arrangement of objects, some of which are indistinguishable. So let's see if we can scale that up to a few more letters that repeat. So Mississippi is a classic example. So I believe this is 11 letters. MIS, SIS, SIP, PI. So again, without any of the, if these were distinguishable, there would be 11 factorial arrangements of those letters. But as we saw in the problem above, we're overcounting by all the arrangements of the indistinguishable letters. So we only have 1 M, that's good, but we have 4 I's. So we're overcounting by 4 factorial with the I's. We have 4 S's, so we're overcounting by all the arrangements of the S's. And we have 2 P's, so we can divide out 2 factorial. So that's pretty much the idea, which we can see again in our very last example of a range. This time we have 7 letters, just like in propose, is that right? Yep, 7 letters. So we start with the arrangement as if they're distinguishable, and then we divide out all the arrangements of the repeats. There's 2 A's, 2 factorial, there's 2 R's, 2 factorial, and I think that's all that repeats. Pretty straightforward. If you have any questions, email me. All right, let's look at number 9, which if we weren't in this scenario, we might not easily see it as the same problem, but it really is. So a child has 12 blocks, of which 6 are black. So I could even write that. B, 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 B. So 6 B's. 4 are red, so 4 R's. 1 is white, W, and 1 is blue. If the child puts the blocks in a line, how many arrangements are possible? So once we write it this way, we see that it's really the same problem as number 8. We're looking for all the words or strings of these letters. We can represent the blocks as letters, where many of them are indistinguishable. So we know we have 12, so if they were distinguishable, we would have 12 factorial of them. And then we're going to divide out all the permutations of the repeats. So we're going to divide out by 6 factorial, 4 factorial, and we could divide out by 1 factorial and 1 factorial. We don't because that's just 1, but to be complete, that is what you're doing with all arrangements anyway. Okay, let's move over to 10, which has got some differences, and let's see if we can tackle those. All right, so we start with 8 people that can be seated in a row. Well, in the first part, we have no restrictions, and we assume these 8 people are distinguishable. Then this is just the same thing as arranging 8 distinguishable letters. So hopefully, as we practice these countings, you start to recognize that we are seeing the same problem over and over and over. All right, so now B, persons A and B must sit next to each other. Okay, so if we have 8 seats with 8 different people, we're putting this restriction that A and B must travel together. So you really can think of it as that's 1 spot, and then we have 2, 3, 4, 5, 6, 7 remaining spots. So we're really going to permute those 7 groups. It's just one of them happens to be glued together. We've seen a problem like this already before as well. So if we're hasty, we might go, oh, we've solved it. It's just 7 factorial. But there is one more thing that can happen, and that is A and B can permute as well, right? So AB is different than BA, so we have 2 factorial for every arrangement of the 7 factorial. Okay? So that's B. All right, I'm going to erase this because, so pause it if you need to, but I need the space to write out for C. So erase. Okay. So now we have 4 men and 4 women, and no 2 men or 2 women can sit next to each other. So really what that's saying is that they must alternate. So, right, we have an even number, 1, 2, 3, 4, and either men start first or women start first. So if a man starts first, so there's M1, then we know that we have another man there, another man there, another man there, and then we have woman 1, woman 2, women 3, women 4. That's the only seating of gender that we can have if men start first. So once we've decided that, so man first or woman first, well, we have 2 choices there, so we'll say 2 choose 1. That is the step of choosing who goes first. Once that's fixed, well, now it's just arranging the men in their respective gender assigned seats and arranging the women. So we have 4 factorial ways to arrange the men, and then 4 factorial ways to arrange the women. All right, so this first step is choosing who goes first. We have 2 ways that can happen. Then once that's decided, where men sit is fixed, and we just have to permute them and permute the women. All right, so that's the answer to C. All right, now I'm going to, I'll just write it over here, D, because I feel like we have room. So this next one is there are 5 men and they must sit next to each other. Okay, so this is very similar to B. So our men now get glued together. So 1, 2, 3, 4, 5. They become 1 unit. And then we have the, so we have 8 people still. The remaining people are women. So what we really have are 4 groups. The glued together men, 1 woman, other woman, other woman. So as we saw above, there are 4 factorial ways to arrange those 4 groups. But just like we could switch the A and B around, we can, wherever the men group sits, we have to permute all of their orders. So there are 5 factorial ways for each grouping of the 4. Excellent. All right, let's look at E. There are 4 married couples and each couple must sit together. All right, I bet you all can do this on your own. What we really have are just 4 groups where we have husband and wife team within each, husband and wife, husband and wife, husband and wife. So we certainly only have 4 groups. We are going to arrange those 4 groups, of which there are 4 factorial ways to do that. And within each arrangement of them, we can permute each pair, right? So this first pair, wherever it sits, we have 2 ways we can sit it in its group. Same for the next, same for the next, same for the next. So this is our answer to E. This was our answer to D. This is our answer to C, B, and A. And that's it.